Hey guys, welcome back. We're continuing our study of random variables, kind of looking at skydiving, I suppose, or at least thinking about skydiving. It is a random event, so every time you go skydiving, we know what can happen, but we don't know what will happen. We know the probabilities overall in the long run of the incidents that happen, I suppose, with skydiving, which would be terrifying. But we know, like in the long run overall, how many times parachutes have failed or something like that. But we don't know the chance. We don't know the outcome of what's going to happen if you go skydiving. So, have you got your life insurance policy yet? one way of thinking about it. All right, so let's talk about rolling a dice. So if we graph out the probabilities of rolling a dice, there's obviously 6 different sides that we have. And each one of those probabilities should be even. They're all independent events, right? Every time you roll the dice, each roll is going to be independent of the next roll. It's not like the dice remembers what happened before that. So if we graph out, this would be an example of a discrete random variable because we know all the possible outcomes and their probability models, so their probabilities as well. So there are 6 outcomes, so the probability is 1 out of 6 for each one of them. All the sample space of the outcomes are going to be 1 through 6. And if we want to find the expected value, so like the average dice that you would roll, the average overall, that would be just the expected value. We take the sum of the payouts times their probabilities. So the payouts are the outcomes, which are 1 through 6, and then their outcomes, their probabilities are going to be 1/6 of all those. So if we add up 1 plus 2 plus 3 plus 4 plus 5 plus 6, that would give us, I guess I can do that real quick. So that's 7, 7, and 7. So that's 21. And then if we divide that by 6, 21 divided by 6 is 3.5. So just did that part in my head. But anyway, so the average would be 3.5. That's our expected value. If I graphed it out here, we'd have our outcomes of 1, 2, 3, all the way through 6, right? Each one of them has a probability of 1 out of a 6. And so if we look at this, the average between those, of course, is going to be the 3.5, which is the mean that I'm graphing out right here. Then the next part that we might be interested in, so our mean we said was 3.5. The next part that we might be interested in is the variation. So the variation is going to be the sum of the squared deviations, then we divide it by the number that we have, or multiply them by their said each individual probability, which would be by doing the same thing in this case, because all the probabilities are equally as likely. All right, so each one of them, the deviation from the mean for the first one would be 2.5 less than what we expected, so that's a 2.5. And then a 2 would be 1.5 less than what we expected, so that's a 1.5. The reason I didn't make these negative is because I'm going to square them anyway, so the deviations being negative wouldn't matter. 3 would be half less than what we expected, and then it'd be a half more, 1.5 more, and then 2.5 more. So those are all the deviations from the mean. We would square all of those and then divide it by 6 by the number that we had. The reason it's just divided by 6 because all the probabilities are exactly the same, so we could factor out that 1/6. So that's going to be 17.5 divided by 6, which is 2.9. So the amount of variation that we would have in rolling a dice with the 6 possible outcomes would be 2.9. Then if we want to find the standard deviation is simply the square root of the variation. So the square root of 2.9 is actually going to be 1.7, if I remember. Yeah. So we have a mean of 3.5 with a standard deviation of 1.7. That's the part we usually remember. We usually don't talk about variation. It's kind of like an intermediate step. But we will talk about it today, of course. So just remember, when you roll a dice, all the outcomes 1 through 6 are all equally as likely with a probability of 1/6. The average dice we would expect to get would be 3.5 with a variation of 2.5. More likely we would say the standard deviation of 1.7. Okay, and also remember how we calculated those deviations. It's kind of a nice visual for what's going on here. All right, so let's say that we want to look at our first thing, which is shifting. So we're going to take the event A, and whatever outcome we get from the dice, we're going to add 2 to it. So we start out with our 1 through 6, but if we shift it, we're just going to add 2 to each one of them. So our lowest one, 1, would now turn into a 3. Not the one I was trying to grab. That would turn into a 3. And the highest one of 6 would now be an 8, right? So the whole distribution just got shifted over to the right 2. So what would that do to our expected value? Well, our mean used to be at 3.5, but now it's just going to be 2 larger than that, right? Which is now going to be 5.5. Our variation, or any measure of the spread, whether we're using variation, which is in squared units, or standard deviation, which is in the actual standard units that we would be dealing with the number itself, would be just the same, right? Because the spread is exactly the same. We just shifted the whole distribution to the right. So our variation and our standard deviation is the same. And the reason for that is because those deviations from the mean are still the same. You didn't introduce more spread when you added 2 to each one of the outcomes. So our rule for shifting, we take our expected value, the expected value for the original x event, the x outcome from event A, plus or minus our constant, would just be taking the expected value and then adding or subtracting that constant. So it's just going to shift it to the left or the right. The expected value, that mean, is going to be shifted to the left or right by whatever the constant was that you added or subtracted. Now with the variation doesn't change, right? The variation stays the same because the spread is still the same. So the variation just is still the variation. We just ignore the c, the constant that we add or subtract. It doesn't change the variation when we're shifting. All right, so what about scaling? So let's say you roll a dice, and whatever outcome you get, whether it's 1 through 6, we double that outcome. So now our lowest value is a 2, the highest value is a 12, and all the possible outcomes we would have would be the even numbers, right? So it could be 2, 4, 6, 8, 10, or 12. Because we're doubling it, none of them could be even. So the numbers 1 through 6 now turned into 2 through 12. So that's the scaling, which is in blue here. So what happened to our mean? Well, the mean is going to be doubled, right? So it's actually going to be centered at 7 this time. And so we just multiply 2 times whatever our constant is times the original expected value. So in this case, it was 7. And then the variation, if you notice, our variation is actually going to be larger because it's spread out more. Our deviations are going to be doubled. And so whenever our deviations are doubled, so then whenever we square them, our variation is going to be multiplied by 4, or whatever our constant is squared, because we're squaring whatever that constant is that we scaled it by. So this is going to be 4 times the size, 4 times the amount of variation we originally had. But if we would have scaled it by a scale factor of 3, then it would be 3 squared, which would be 9 times the variation that we had originally. And then when we take the square root of variation, that'll give us back to the standard deviation, which is going to be 3.4. And the standard deviation is actually, interesting enough, it's going to double, because when we take the square root of something that was 4 times as big, it's going to go back down to just being 2 times as big, which is kind of interesting. So the standard deviation got doubled, but the variation got quadrupled because it was the doubled squared when we're dealing with variation and standard deviation. So if you notice, before we had a standard deviation of 1.7, now we have a standard deviation of 3.4, and then we have 4 times the original variation as well. Okay, so shifting the expected value is just going to be shifted plus or minus, and the variation and standard deviation is not impacted because all it did was it moved it all to the right, or moved it to the left, or whatever's going on. And then whenever we scale it, everything gets multiplied by the scale factor, except for the variation is multiplied by the scale factor squared, because variation is dealing with deviations squared. All right, so what about adding 2 random variables? So now instead of whatever dice you roll, I double it, now we add them together. So it's possible to get odd numbers. So this one's clearly different. The sums can be anything, like that one's 7's an odd number. In fact, 7 would be the most common one that we would roll a sum of. In fact, I bet within 6 rolls, I'm likely to get another one. At least that's what, see, I did another 7. So 7 is the most common. We'll actually map that out. It's a triangular distribution. It's beautiful. We're going to do that today. Normally we get to do it in class. It's a little bit more fun, but we'll do it on the video. So what about adding 2 random variables? So each time we roll a dice, it's its own independent random variable. If we add the sum of those dice, now our range of values is going to be anywhere from 2 to 12, which is the same range of values that we could have had when we doubled it, but now it's possible to get odd numbers. So let's go ahead and see what that looks like when we graph it out. So first we need to kind of look at what happens when you take the sum of 2 dice. So the sample space is all the possible numbers from 2 to 12. That's all the possible sums of two dice that we could get, 6-sided dice. What's the probability of rolling a sum of a 7? Well, that's all the possible outcomes. There are actually 6 different ways to roll a sum of 7. If you think about it, no matter what you roll for the first dice, there's always one dice roll that would pair up with it to get it to go to 7, because 1 plus 6 would go to 7, 2 plus 5, 3 plus 4, 4 plus 3, 5 plus 2, 6 plus 1. So whatever the first dice is, there's always one that the second dice would have to match with it in order to make it roll to a 7. So the probabilities of rolling 7 is 1 out of 6. But what's the probability of rolling a 2? Well, the probability of rolling a 2, there's only one way of doing it. That's to have outcomes of 1 and 1, or snake eyes, right? Same thing with rolling a 12. That's the rarest. Same with rolling a 2, a sum of a 2, because there's only one combination that'll do that, which is 2 6s. But what about rolling a 5? Well, you can have a 1 and a 4, a 2 and a 3, 3 and a 2, and a 4 and a 1. So there's 4 ways to roll a 5. So if we go ahead and fill in this chart here, which I think I might have given you on the assignment. No, I didn't. Okay, so just watch me do it and it'll be just fine. So on this one, here's our event A and here's our event B, and then the cross of those two is going to be the sum. So 1 and 1 is 2, 1 and 2 is 3, 1 and 4 and 3 is 4, 5, 6, 7. You see how that all works. 2 and 1 would be, I suppose I'm supposed to rule this down, would be 3, and then 4, 5, 6, 7, 8 now, because we're adding one more. And you can probably guess what's happening here, and you'll start seeing a pattern with the diagonals, don't you? So the diagonals are always going to be congruent. There's only one way to roll a 12 and one way to roll a 2, and you got 2 ways. So 1 out of 36, because 6 times 6 would be 36 possible combinations. So 1 out of 36 is the probability of rolling a 2. There are 2 ways to roll a 3. There are 3 ways to roll a 4. There are 4 ways to roll a 5, 6 ways to roll, or 5 ways to roll a 6. It's just one less than the number, right? Then the most is going to be this diagonal, which is 6 ways to roll a 7, and then it goes right back down. So then it goes to 5 out of 36, 4, 3, 2, and then back down to 1. So when we graph it out, we actually get a shape which is a triangular distribution, and it's called that because it's the shape of a triangle. So we go from 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, and then 1/6, which is 6 out of 36, and it goes right back down. Okay, so unlike multiplying it by 2, which had an even, probability going across, which is the blue one here, and the spreads would actually be, the variation would be higher as well, because we're just as likely to get a 12 as we were to get a sum of, or basically not a sum of 2, but a dice multiplied to get to 8 or to 6, right? All of those are the same probabilities, but getting a sum of 12 is rarer than getting this one. So we're going to have less variation is what I'm trying to show. But how much less variation would we have? Well, that's a really good question. First, let's just think about the sum, the center, the sum of A, the two events A and B is going to be the sum of the individual expected values, which is 3.5 for each dice. So 3.5 plus 3.5 would be 7. So it is still centered at 7, just like scaling by 2. But if we scale by 3, it would be centered at, that would be 10.5, right? Because we would multiply it by 3. So same thing if we added 3 dice together, that would be centered, the sum would be centered at 10.5. The standard deviation, I think I'm just going to give it to you, but anyway, it's 2.4. And then the variation is going to be 5.8. Now, if we're looking at the variation and the variation of the original event, which was 2.9, do you notice a pattern between 2.9 and 5.8? Like, think about like multiplying it by 2 or adding it together. So we were able to add the expected values together, right? 3.5 and 3.5 is 7. If we add the variations as well, 2.9 plus 2.9 would give us to the 5.8. So when we have independent events that we're adding together, the sum or the difference between, if we're subtracting, it will give us the same thing. The variation will add. The standard deviation is actually going to be the square root of the sum of the variations. So the pattern that we're actually getting with the standard deviation is something that you've actually seen before, and it's related to the Pythagorean theorem, which is really cool because I teach geometry as well. Some of you guys even had me for geometry. So this is a visual of what's happening with the Pythagorean theorem. So 3 squared, if we make a square out of lengths of 3, plus the 4 squared, the sum of the lengths of 4 that have been made into a square, is going to be equal to 5 squared, right? So 25 is equal to 9 plus 16, right? That's what's being shown here. Now, this only works when it's a right triangle. just like the Pythagorean theorem of statistics only works when it is an independent event, which is really fascinating. So what we're doing is we're taking our links here, which are similar to our standard deviations, and we square them to get them to the variations, and then we can, once they're at the level of variation, we can add the variations together. So this is what it looks like if we did the Pythagorean theorem, I suppose, of statistics visualized. We take the standard deviations of our first event plus our standard deviations of our second event. And we actually square their standard deviations to get their variances, and then we can add the variations together. So yeah, really cool. And then to go back down to the standard deviation, we take the square root of it. So 3, 4, and 5, the same thing. Standard deviation of event A squared plus standard deviation of event B squared is equal to the standard deviation of the sum of the two events squared. And then to get back to the original one, we would take the square root of it to get back to the actual standard deviation, which is pretty cool. All right, so here are the values, our actual values. So rolling a dice had a standard deviation of 1.7. So 1.7 squared plus 1.7 squared would give us the 5.8. Then we take the 5.8, the square root of that would give us a standard deviation of the sum of the two events of 2.4. The other way you can look at it is just summing the variations. So the variation for each dice was 2.9. So the variation we had for the first event plus the variation of the second event would give us a total amount of variation for the sum of the two events, which would be 5.8, which is fascinating. And again, that only works when they're independent. So just like a Pythagorean theorem only works whenever we have right triangles, the two events have to be independent. If there's any sort of covariance between the two, whether they are positively or negatively associated with each other, like direction of the association, just like this would change if we had a Pythagorean theorem. If this was an acute triangle or an obtuse triangle, that would either increase or decrease the variation between the sum of those two, not just simply adding their variations together. So you got to be careful. So when we shift constants, our expected value shifts with it, just like we would move the center, okay? But the amount of variation, the whole distribution is just shifting over. It's not growing. So the standard deviation and the variance stay the same. They remain unchanged. So the expected value plus the constant, you just take the expected value plus the constant, but the variation is not impacted by shifting. When it comes to scaling, we actually just multiply everything by whatever the scale factor is, but with variation, it's going to be the scale factor squared because variation is taking the deviations and squaring those deviations, the sum of the deviations squared. So we went from 3.5 for expected value to 7. Our variation was quadrupled because it was 2 squared. And then our standard deviation was just multiplied by our scale factor. And notice that it's twice as spread out, so our standard deviation is twice as spread out. It's a good way to remember it too, if we're multiplying by a scale factor of 2. Scale factor of 3 would be times 3, and then 3 squared would be 9 for the variation. But whenever we add or subtract them, it's not the same equal probabilities like we would if we were doubling them. Now it's going to kind of regress back towards the mean, kind of in a sense, and we have this triangular distribution that's showing up and the Pythagorean theorem of statistics. So what's kind of cool about that is the variations add, like we just said. So 2.9 plus the 2.9 from the two random events would give us a total amount of variation of 5.8. Then we take the square root of that. They'll tell us the standard deviation, just like taking the square root of the Pythagorean theorem to get back to the original units, just like we see here. So whenever we add or subtract the standard deviation of two random events, we just do the Pythagorean theorem, or you can add their variations because the variations are already squaring those side links. All right, let's look at number 19. The probability model shows the number of repair calls that an appliance shop may receive during an hour. So we want to put this in the calculator to solve for the expected value. So I'll show you the easier way. So we'll go to stat and then edit, and list 1, we're going to put all of our outcomes, which are 0 repair calls, 1, 2, or 3. And then the next list, we're going to do the probabilities for each one of those. Okay, and then let me just show you the easy way to do it. So what we're going to do is we're going to go to stat and calculate one variable stats, just like we did before. Our frequency list is telling us the actual frequencies or the probabilities of each one of these from our probability model. So we have our outcomes in list 1 and their respective frequencies in the same order. Do make sure those lists match up. Then we hit calculate. That'll give us an average of 1.7. So that means our expected value is 1.7. So On average, the appliance shop, we would expect them each hour to receive, on average, again, 1.7 repair calls. With the standard deviation, at the sigma of x is equal to 0.9. The reason this is sigma of x is because it's Greek, where we have all the possibilities, the whole population. So we're using population parameters instead of sample statistics. This doesn't come from a sample, so there's one less degree of freedom. So anyway, that's why the s of x is missing, it's blank, because it's not from a sample. So we're going to use the sigma of x. Yeah, so we pretty much have everything we need to know from there. That saves us a lot of time. Well, if our average was 1.7, the deviation, if we had 0, that means we had 1.7 less than we expected, so that would be a negative 1.7. If we had 1, that would be negative 0.7 less than what we expected, and this would be 0.3 more than we expected and 1.3 more than we expected. So all we're doing is we're taking our observation minus the mean, so the amount we actually had here minus what the average was, which was 1.7, so that's why this one was negative. All right, calculate how many calls they would expect. So that was the sum. You can do the sum of the probabilities, or the payouts times their respective probabilities. That's where we get the 1.7. But the calculator did it for us, so we don't have to. To find the variation, we just take the deviations and square them. So the observation minus the mean squared. Then we multiply them by the respective probabilities because they're not all equally as likely. This 2 was the most likely, so, and 0 was pretty rare. We found the variance. They told us the standard deviation was 0.9, so the variation would actually be 0.9 squared, which would be 0.81. In case you're wondering how to do that. So yeah, variation is 0.81, standard deviation was 0.9. We take the square root of 0.81 to get to the standard deviation. How many calls should they expect in an 8-hour workday? All right, so an 8-hour workday is 8 separate hours. Each hour is an independent event. So it's not like whatever happened on the first hour, we multiply that times 8, and then that's what we're expecting. No, because some of them are going to be higher, some are going to be lower. They're all independent events. So what we're really doing is we're not shifting or scaling. It's not like we're just multiplying it by 8 or adding 2 hours to our first one or something like that. But we're actually adding independent events. So we have to do the Pythagorean theorem of statistics. How many we would expect? Well, we expect 1.7 on each one of them. So we would just add 1.7 plus 1.7 plus 1.7. We would do that 8 times, which is really the same thing as 8 times 1.7, which would give us 13.6 calls. The standard deviation, remember we can't add standard deviations, instead we add the variation. So we're doing the Pythagorean theorem, but with like 8 different parts. So I'm going to convert it, or just use the variation and then multiply that. So the variation for the first hour would be 0.81, and then there's 8 of those hours, right? So I'm going to multiply that by 8, or just 0.81 plus 0.81 plus 0.81 for all 8 of those hours. Now this is the total variation we would expect in an 8-hour work day. If I want to go back to the standard deviation, I just take the square root of it. So caret 0.5, which would give me 2.55 if you want to round. What assumption did we make in calculating the variance of the random variables? Well, in calculating the variation or the standard deviation, we're assuming that each one is independent. Just like with the Pythagorean theorem, we're assuming, or we have to know, that it's a right triangle. If they're not independent events, if there's any sort of covariance between the two, then we can't do the Pythagorean theorem of statistics. We have to do other methods, which are beyond the scope of this course. You have to learn that stuff in college. So yes, we're assuming that they're independent events. All right, 20. A commuter must pass through 5 traffic lights on her way to work and will have to stop at each one that's red. She estimates a probability model for the number of red lights she hits as shown below, from 0 lights red all the way to 5, and then the probabilities are shown here. How many lights would she expect to hit in each day? So we're going to just put this in the calculator again. We're not going to do it all by hand. So the possible outcomes are 0, 1, 2, 3, 4, and 5, and the probabilities are given. All right, looks good. So once I put those in here, make sure they're lined up. Just go to stat, not stat edit, stat calculate. So arrow over to calculate, one variable stats. Good to go. All right, so the average would be 2.28 or 2.29 if you want to round. red lights with a standard deviation of 1.24. So how many lights would she expect to hit in a typical 5-day work week? So just like the last question, each day is going to be an independent day. So just because she hit 3 lights on Monday doesn't mean she's also, we can't just multiply it by 5, because then we would be assuming that we would hit 3 on every one of those 5 days. So can't do that. Instead, each one of them is an independent event. So we would basically add the expected values times 5 times, which is the same thing as multiplying. But the real difference comes into play with the variation and the standard deviation. So we're not just multiplying the standard deviation like we would if it was scaling. Instead, we're going to add the variations together, or do the Pythagorean theorem of statistics for the standard deviation. So I prefer to work with just adding the variation, so that's a lot easier. So for the expected value, we would do 2.29, which is our rounded value, times 5. Which would go, so basically we're expecting on an average 5-day work week for her to hit 11.45 red lights with a standard deviation. So I'm going to take my variation and then I'm going to multiply that times 5 as well. But then that's because that was adding it together 5 times, right? That's the total amount of variation that would be in that work week for the red lights. So instead I want to get back to standard deviation, so I got to take the square root of it, which would tell me 2.77. So on average, we expect her to hit 11.45 red lights throughout the week with a standard deviation of 2.77. And again, we're assuming that each day was independent. So if she had heavy traffic on Monday, it doesn't make it more likely to have heavy traffic or more red lights on Tuesday. All right, company selling vegetable seeds packets, seeds in packets of 20 estimates the mean number of seeds that will actually grow is 18, so 2 are defective, with a standard deviation of 1.2 seeds. If you buy 5 different seed packets, how many bad seeds do you expect to get? Well, for the means, each package we're assuming is an independent event. So we would expect 2 bad ones per package, so 2 times 5 would give us 10. What's the standard deviation? So if we have a standard deviation of 1.2, let's go ahead and first convert that to variance. Then we can just add the variances together. So the total variance is 1.44, and we're going to multiply that times 5, because that's adding it to itself 5 times, in other words. But that's the amount of variation we would have, not standard deviation. So then we have to go back to the square root to get it back to standard deviation units, which would be 2.68. So we would expect to have 10 bad seeds, with a standard deviation of 2.68. What assumptions did we make about the seeds? We were assuming that each seed was an independent event, and so if you have bad seeds and more than expected in one, you're not more likely to have it from the other. Is that assumption warranted? It depends on where they got the information about the seeds. It's the seeds you have, whether or not they grow. So I don't know. I mean, you could have a bad year if that was the information we had from last year. Maybe this year the seeds are different. Was making them grow or not grow? Is that the soil that's being used? Is it the other conditions? So as long as as you think it's okay that they're independent, maybe you got a really bad batch from all 5 that you bought from the same store at the same time or something. Maybe half of them were bad in all of them. So it just depends. But yeah, we can probably assume that they're independent events. All right, so that's it. Just remember pretty much today, shifting and scaling and adding variation with the Pythagorean theorem of statistics when we're adding random events together, and you're good to go. Tomorrow we'll come back with our last part from this chapter. And if you have any questions, just let me know. I'll see you later.